Hi, my name is John McKay. I'm currently a researcher from the AFRC, the Advanced Forming Research Centre, situated in Glasgow. Before my research, I previously worked in manufacturing, developing, and researching communications hardware for Google, Facebook, Instagram, and Amazon. Today, I'm going to be talking about electromagnetic coils for next generation machines. I'll then be going over some of the areas of my interest during my research, defining what a high-performance coil is. I'll then talk about advances in materials and manufacturing and how they could potentially have an effect on the design and manufacture of the coils. Lastly, I'll talk about my proposed solution, utilizing advances in manufacturing and machine learning. So currently the world is being faced with the challenge of global warming, climate change, and the move away from fossil fuels. This has sparked a need to electrify our existing transportation infrastructure and demand for alternative technologies. This has meant that there's now a significant interest in electrical machine development with particular focus on efficiency, power density, weight reduction from industries such as automotive and aerospace. My research is part of a larger EPSRC funded project aiming to bring high-value, low-volume electrical machine manufacturing back to the UK with a primary focus on aerospace, with potential benefactors in automotive, transportation and energy. In regards to FEMM Hub, my PhD research belongs to Grand Challenge 2.2, which is a high-performance coils with ultimate control. So electrical machines or electrical motors are really just pieces of equipment which convert electrical energy into mechanical energy for use in doing work. This is achieved by energizing electromagnetic coils, which are the active components inside them, with an electric current. This consequently produces a magnetic field radiating outwards. This magnetic field attracts a permanent magnet. Sometimes it can also be like an opposing electromagnetic coil itself, which has an opposing polarity in terms of magnetic field. This aligns and turns the rotor and hence translates our electrical energy into mechanical energy. So an electromagnetic coil is an electric conductor such as a wire coated in enamel or plastic coating, which is then wrapped to form a coil or spiral or a helical type configuration. So by passing an electric current through the conductor, a circular magnetic field is produced. The reason why the conductor is spun in the coil is because the more number of turns we have, essentially the greater magnetic field is produced, or the flux density. This is because the magnetic field lines are superposed. So my research is centered around a number of areas such as machine types, coil configurations like concentrated coils, distributed coils, hairpins, overcyclic, etc. There are various advantages and disadvantages such as operational frequencies, performance, flux densities, torque. I also study materials such as carbon nanotubes, graphene, carbon nanotube in impregnated copper, aluminium, along with materials for like the starter structure like high silicon steels, soft magnetic composites, for use in minimizing eddy current losses or hysteresis losses. So from materials, I then went into manufacturing processes like winding techniques, insulation methods, forming techniques, all the way to maturing processes such as casting and additive manufacturing like 3D printing. So currently I'm learning how to completely design a machine from scratch, as other areas of the machine can interact with the coils themselves, causing losses to incur, inhibiting their performance. So it's essential that I have like an understanding of how these interactions can occur. Lastly, I'm researching machine learning, as I think it's an incredibly essential skill to have going forward. Understanding how it works and how to actually leverage data science for engineering, I think, is pivotal for success in the coming decades. So I'll be leveraging machine learning as a tool to help me optimize my coil geometries whilst exploring like the possibility space and hopefully getting me to some kind of novel discoveries along the way. So in order to define what a high performance coil is, an understanding of what detriments the coil performance overall has to be achieved. I did this by looking at material properties such as electrical conductivities, their thermal transfer capabilities, weight, malleability, cost. Other material properties like porosity, contaminants like oxygen, carbides, etc. Material structure can also play into like the performance of a coil, either increasing or reducing its performance. An area of interest for myself is the actual geometric design of the coil, such as its fill factor, which is the ratio of copper to slot space, operational frequency, effects like skin effect, proximity effect, eddy currents, thermal dissipation qualities, etc. So also the availability of the coil material is also kind of important. Are there any challenges manufacturing the material? How expensive is it? How readily available is it? Will it degrade over time, or perform as intended? Is there an understanding of how that material actually works? So one of the areas that is of particular interest is in potential future materials. Currently, the industry standard is copper due to its thermal and electrical performance, and it's cheap and it's readily available. So in the search for more performance, higher flux densities, efficiency, and reduced weight, a number of next generation materials are currently being researched. For example, graphene, carbon nanotube impregnated copper and aluminium. They all kind of promise qualities over and above copper in terms of its conductivity and thermal performance, and also mechanical strength. However, these materials are unfortunately not ready to be mass produced in the kind of scales needed for industry, and there's also a number of difficulties manufacturing them. For example, carbon nanotubes have different configurations and need to be aligned correctly like a gun barrel for them to exhibit the kind of superior qualities that the research suggests, whilst graphene is difficult to produce as a single layer, and there's numerous like variants and layering configurations. There's also challenges in removing it from the substrate, and there are no like standard substrates for graphene. It's also really expensive because chemical vapor deposition is currently really the only way to manufacture it. So it's not really possible to produce in high quantities right now. So this has led me on to a potential another area like manufacturing of the coils. So when compared to traditionally wound conductor coils, casting can offer a superior fill factor and current density, whilst potentially enabling greater amounts of autonomy on a production line. For instance, casted coils can boast near 100% fill factor and greater current densities, and could be pre-manufactured and stored later for use. Their precise shape and geometry would aid a robotic manufacturing line, because there's no complex winding strategies being used. Additive manufacturing would enable very precise, highly efficient, and specialized coil geometries that could be made and optimized for specific electrical machines without the need for additional tooling. So currently, additive manufacturing boasts near 100% electrical properties of pure copper, whilst enabling highly custom geometries depending on the method used. There's also like a standard being set for additive manufacturing, such as DFAM, so Design for Additive Manufacturing, which aims at reducing part complexity, part numbers, trying to drive down like production costs and increasing the actual reliability of the part itself. So I'm primarily interested in the geometry of the coils and how their shapes and configurations interact with the variables of my interest. There might be potential designs and geometries which could help us, better achieve greater fill factors. For example, 10% more fill factor equals 1% more efficiency in terms of machine operation, better thermal performance, essentially more efficiency again. By increasing its thermal performance, you can essentially decrease the apparent resistance of the coil. Also, larger bands of efficient frequency operation, and this is due to the fact that with increasing operational frequencies, you get effects like skin effect and proximity effect like taking place, which can further degrade the performance of the coils. And so the introduction with new manufacturing methods such as casting and additive manufacturing, we could design unique and non-orthodox coil geometries which could improve upon the variables of interest, coils which are not necessarily a wound copper wire, but could potentially be any kind of shape or geometry, which would allow maybe even to integrate coil cooling channels into the actual coil itself without degrading the actual performance of the coil. So I'd like to explore as much of the possibility space as I can with respect to the variables of interest, whilst constraining myself to like current industry standards such as like copper and aluminium. This is due to the fact that there are still large challenges associated with the materials like carbon nanotubes, graphene, and they're also really highly cost prohibitive as well. So I'd like to take advantage of the new manufacturing methods such as casting and additive manufacturing because they would allow novel designs and potential new learnings and insights. There's also the possibility of using these methods to create really highly bespoke customized coils on a per machine basis. So my proposed solution is a genetic algorithm in combination with some machine learning, like this unsupervised deep learning stack, which will look at the optimization data and then reconstruct the coil geometry to take advantage of the data produced by the finite element analysis software, using voxels, which are three-dimensional pixels which have information stored inside them. Once a new geometry has been created, it will then be fed back into loop for analysis until a unique geometry is produced, which provides some kind of advantageous quality, or maybe there's some novel aspects to that particular three-dimensional design. So the AFRC is in a kind of unique position in that we currently have access to ANSYS software products. So what this allows me to do is harness industry standard software like MotorCAD, Maxwell, Thermal. Most importantly, I can utilize ANSYS Optislang, which is like an optimization software which uses machine learning to find various kind of solutions. Because all the software is from the same vendor, compatibility shouldn't be an issue, and I can link all the analysis software into a complex kind of feedback loop system through Optislang and build it graphically. This allows me to kind of save time like on iterations and the deep learning stack learning time as well, whilst having a software do the kind of heavy lifting for me. Initially, I intend to apply this to concentrated coils as their geometries are kind of discretely bound and they're not as complex as, say, distributed coils or hairpin style coils in terms of their geometric composition. Concentrated coils will be part of my initial proof of concept stage, where I explore the limitations of the method, the boundary conditions and the amount of samples, and the construction of the overall algorithm itself. So just quickly going over the actual analytical process. So firstly, we have like a base 3D geometry created and prepared for analysis. This will be supplied to me by Stephen J. Forrest. This geometry is then finite element analyzed as a series of stacked 2D analysis interspersed with full 3D analysis. This is primarily for speed, as 2D topological simulations can take minutes, while as a full 3D analysis can take tens of hours, and so it's imperative that as much data as possible can be fed into the algorithm, whilst trying to retain as much accuracy as possible. The 3D geometry is then voxelated So this allows the algorithm to rearrange the geometry in such a way as to either improve or express a particular quality that it might have found inside the data itself. It just makes it easier for the algorithm to actually switch certain parts of the volume on or off, essentially. So instead of using a very complex set of three-dimensional points, you have very simple, discrete little building blocks. So finally, the novel voxelated geometry is produced, expressing whichever qualities that it's found inside the data, and then this is then converted back into a 3D model capable of being FEMM analyzed further or iterated upon further. I can also study this particular geometry myself to see what kind of qualities that particular configuration has. So as an example, as you can see, the kind of potential outputs that could be had on the left, you have a very low resolution geometric data representation. So if I were to use a very small amount of voxels, then you might have something that looks like that on the left. Or if I were to use a very high number of voxels, then you might have a very almost kind of organic looking geometry being produced, but it's just purely for illustration purposes. I'm not particularly sure what the algorithm will produce on the other end, but it will be physically accurate according to the kind of the theory. Right, so moving forward over the coming months, I'll be producing a proof of concept solution using ANSYS software and Python. However, I do have MATLAB as a backup, just in case Python doesn't particularly work out. This is to produce, novel concentrated coil structures, exploring the possibilities and the process and understanding its limitation and boundaries. For instance, one of the limitations of actually manufacturing these coils is that with additive manufacturing is that the smallest kind of unit or feature that can be expressed is 0.5 millimeters squared. So this is really just a limitation that needs to be taken into consideration. So maybe perhaps a single voxel could be 0.5 millimeters squared in terms of its dimensions, and so that would dictate how many voxels that could be expressed within a very kind of discrete bounding volume inside the slot for a concentrated coil. I'll then be taking a look at the structures generated to see what is novel about that structure, or what effects are actually taking place, and how those effects may be minimized. How does the generated structure characteristics compare to traditionally designed wound copper coils in terms of fill factor, thermal performance? How does it actually reduce skin effect, proximity effects? How does hysteresis actually behave with that particular configuration? And its thermal performance as well. Can we optimize it to actually perform better? So ultimately, I'll be exploring whether or not I can actually manufacture the coil. What its limitations are. Does it improve upon a standard wound structure? I'll be aiming to look at manufacturing a coil, running tests on it, analyzing how the actual additive manufacturing process affects its performance. Can I manufacture the coil itself, or are the designs being generated unable to be manufactured in real life, essentially? So this is just some of the activities that I plan to do moving forward on the project over the next coming months. After I finish concentrated coils, maybe hopefully I can move on to distributed coils, hairpin coils, or maybe even move further into superconducting coils as well for superconducting machines. So thanks very much for watching my presentation. If you have any questions, please feel free to ask me. Thanks again.